In this video, we're going to look at the concept of the derivative. Now, as we develop that concept, we start with the concept of rate of change. So in our little box here, we're going to write that for y equals f of x, the average rate of change so this is very important. Should have capitalized. But the average rate of change from x equals a to x equals a plus h will be this rational function, f of a plus h minus f of a over a plus h minus a. Now this is the same really as slope, because you have a y value minus a y value over an x value minus another x value. So this is really the same slope, and this function simplifies to f of a plus h minus f of a over just h, because those a's cancel out. And we have to add the caveat that h doesn't equal 0. Let's look at this in example 1. In example 1, we're talking about the revenue in dollars from the sale of X plastic planter boxes. So this function here is the revenue function. So you can see here, if you sell 400 planter boxes, it looks like you're going to have a revenue of a little bit less than $5,000. This asks, what is the change in revenue if production is changed from 100 planters to 400 planters? So we want to know the change in revenue. So that would be R of 400 minus R of 100. So the revenue at 400, which we're just looking at here, minus the revenue at 100, which would be here. Let's calculate those values. Plugging 400 into my revenue function gives me $4,800. And plugging 100 into the revenue function gives me $1,800. So the change in revenue would be the $4,800, $4,800 minus $1,800, which is going to give me $3,000. So what is the average rate of change in revenue from this change in production? So average rate of change from above is the y value minus the y value, which we just did. So that would be the 4,800 minus the 1,800 over the x values, which would be the 400 minus the 100. See how similar this is to slope. So this gives us 3,000 over 300, which is going to be 10. Let's see if we can figure the units. Up here we have the units of dollars, and this is the number of planters. So the units on this would be $10 per planter. Let's interpret this graphically. Let me draw a line from those 2 points. Drawing a line between these 2 points, what we notice is that what we've calculated here at the $10 per planter, interesting, is the slope of that line. Let's move on to example 2. Example 2 states that a small steel ball dropped from a tower will fall a distance of y feet in x seconds, as given approximately by the formula y equals f of x equals 16x squared. Now, for the purposes of this problem, we are going to consider that y is positive, even though it's falling downward. If we want to find the average velocity, that's the same thing as average rate of change. So, average velocity is the same as average rate of change. Oftentimes when we refer to average rate of change, we just use ARC to talk about average rate of change. So that's what we're going to do here. Now the average velocity from 2 to 3 would be f of 3 minus f of 2 over 3 minus 2. So if we substitute 3 into this function, we have 16 times 3 squared minus 16 times the 2 squared. That'll give us our y values over 3 minus 2. Let's calculate that and figure out what it is. When we substituted those values in, we got 144 was the same as 16 times 3 squared. 16 times 2 squared was 64. Subtracting those and putting them over 1, we get 80. Now let's see what units we should use. It's y is in feet. So in our numerator, we're talking about feet. And in the denominator, as our x values, we're talking about seconds. So this is 80 feet per second would be the average velocity from 2 to 3 seconds. Then it wants us to find the average velocity from 2 to x equals 2 plus h seconds. So plus h, that's our highest value. So we'll be finding f of 2 plus h minus f of 2 over 3, not 3 minus 2, would be 2 plus h minus 2. This is exactly what our formula said from above. All right, f of 2 plus h means we're going to substitute 2 plus h into the 16x squared. So it's going to look like this. Then f of 2, we found that above to be 64. So we can straight over 2 plus h minus 2. Now, this is where we find students make mistakes quite often. You cannot distribute the 16 to the h. You must do the 2 plus h squared first. I'm going to do that over here. 2 plus h squared means you're squaring the whole binomial, and you have to FOIL it, for lack of a better term. So 2 times 2 gives me 4. 2 times 2h is 2h. And here we'd take h times 2, which is also 2h. And then h times h gives me that h squared. Combining like terms, we're going to get 4 plus 4h plus h squared. So that's what this is. So going back to our calculation down here, we're going to write 16 times 4 is 4h plus h squared. And then that will be minus the 64 over. Now down here, 2 plus h minus 2, those 2's are going to cancel and just give us h. We have to clean this up a little bit. When we do, we multiply 16 times all of these terms, so we'll get 16 plus 16. We won't get 16. We'll get 64, because 4 times 16 is 64. So we're going to get 64 plus 64h plus 16h minus 64 over the h. We can clean this up because the 64s will cancel. So in simplifying this one should be h squared. What we have now, sorry to run out of room here, is the 64h plus 16h squared over h. We can take this one more step because both of these terms have an h in it, which can be factored out, leaving us with 64 plus 16h over h, and those can be canceled. So the average velocity from 2 to 2 plus h is going to be this 64 plus 16h. 16h. And that would be in feet per second. Now, we know that that answer has a variable in it, but it has a variable in it because they're not being specific about the second that they're talking about. Going from 2 seconds to 2 plus h seconds, so that average velocity will be 64 plus 16h feet per second. Now it asks me to find the limit as h approaches 0. So we're going to write that this way. The limit as h approaches 0 of this answer we got in part B of 64 plus 16h. If h is approaching 0, 16 times 0, we can do that here, we're just going to get 64 feet per second. Now discuss the possible interpretation of the limit from part C. Well, as h approaches 0, what we're talking about is the slope of this function at x equals 2, because the distance between the 2 points is approaching 0. So graphically, the interpretation is the slope at 2. But according to this problem, since we're talking about the average velocity here, what we're actually getting is the instantaneous velocity, 2 seconds. I wish I could spell that correctly. The instantaneous velocity at 2 seconds after the ball is released. All right, in our next video, we will look at more interpretations of the derivative. Thanks for watching.